Hi everyone, in this video we are going to cover section 5.5 titled Substitution, and it is also sometimes referred to as U-substitution. U-substitution, there we go. Alright, so the theorem here states substitution with indefinite integrals, although it's similar for definite integrals. We'll get into that later in the video. So we define a function u equal to g of x, where g prime is continuous over some interval. F of x is continuous over the corresponding range of g, and let capital F be an antiderivative of little f, similar notation to what we've used. So then the integral of f of g of x, so notice we have a nested function there, times g prime. So inside of the integral is our g function and its derivative g prime. All right, so the antiderivative of that is also the same as f of u du. So we're changing variables here. We're going from nested functions in terms of x, making a substitution, and getting a new function in terms of u, a new integral in terms of u. All right, and the antiderivative is capital F of g of x plus a constant, because these are indefinite integrals. Okay, so if that is challenging to understand and abstract, let's take the derivative. So let's understand this by taking a derivative of this answer. So if I want the derivative of f of, f of g of x, two close parentheses, I want to take the derivative of that. Now we all hopefully remember the chain rule. The derivative of this is the derivative of the outer function times the derivative of the inner function. So the derivative, so I didn't write the plus c because the derivative of a constant is 0. But the derivative of this function, we take the derivative of the outside, keep the inside the same, times the derivative of the inside. And hey, look at that. That is exactly what we started with inside of the integral. So the derivative of the answer is what's inside of the original integral. And I have it as capital F prime, but that's the same as little f. So long story short, what U-substitution essentially does is it's a means of integrating and undoing the chain rule. U-substitution is how we undo a function whose derivative is determined by the chain rule. Okay, so let's look at an example, because that's kind of out there. So let's see what it looks like in practice. So we have this using substitution to find the antiderivative of the integral of 6x times 3x squared plus 4 to the 4th power dx. Now, we could expand out all of this algebra, and it would be terrible. There would be lots and lots of terms. The algebra would be challenging, but we could distribute all this out and be okay and take the antiderivative of each term individually. But since it's to the 4th power, that's just not good in practice. So what I want you to look at here is inside of the parentheses to the 4th power is 3x squared plus 4, and outside of the parentheses in front of that is 6x. I'll pause my talking here for a second. What do you notice about the relationship between those two things? If you're thinking that 6x is the derivative of 3x squared plus 4, that's totally awesome. And that's the connection that you need to see within this section in order to be successful in doing these problems. So I can tell that the derivative of 3x squared plus 4 is 6x. So to evaluate this antiderivative, we're going to say let u, we're going to introduce this u function, equal 3x squared plus 4. U is the thing that I see its derivative inside of that as the other term. It's also the thing that has the challenging algebra. It's that thing to the 4th power. All right, and then the way we write this next step is du, the derivative of u, is equal to 6x, and I'm not going to write plus 0, but the derivative of 4 is 0, 6x times dx. Now, what I just wrote there, that is equivalent to writing du over dx is equal to 6x, but we've essentially multiplied the dx on the right-hand side, because what our goal here is to take everything inside of the integral that is in terms of x and write it in terms of u. So I'm going to circle, let's see, what color do I use? I'll use red. This 3x squared plus 4 that I am circling, there it is. That's not red. This 3x squared plus 4 right there that is going to substitute and be u. And then the 6x dx, 6x dx is going to substitute to be du. All right, so our integral of 6x times 3x squared plus 4 to the 4th power dx. Notice I'm not substituting the 4, the exponent in the 4. That's staying. That is equal to the integral of u to the 4th power du. U equals 3x squared plus 4, so that went there. Du is equal to 6x dx, so those two terms went there. So we've taken everything in our integral in terms of x, and written it in terms of u. That's the goal in that step. And now we're left with an integral that's pretty straightforward to take the antiderivative of. This is equal to u to the 5th over 5 plus a constant c. Boom, that's it. Well, that's almost it. We do have to go back to x. All right, so if our question starts out in terms of x, we need to write our answer in terms of x. So we put our x back in. U is equal to 3x squared plus 4 raised to the 5th power over 5 plus our constant c. And I'm not going to do it well, actually, no, I will do it in this video. If we take the derivative of that answer, let me put it off to the side here. If I take, let's put it in red because it's a check. If I take 3x squared plus 4 raised to the 5th power over 5 plus c, I want to take the derivative of that, so I'm just putting the prime outside. Well, the derivative of our constant is 0. The 5 comes down. 3x squared plus 4 to the 4th power over 5. Need a little bit more space there. And then we have to use the chain rule times the derivative of the inside, which is 6x. 5's cancel out, and hey, look at that. What you're left with there is what the integral was originally evaluating. Okay, so that's how we use the chain rule, or excuse me, use substitution to undo the chain rule. We have a problem-solving strategy when using use substitution. You can read through these. They're also in OpenStax. I am not going to read them out loud for you, but this is just some steps to follow through, hopefully making the process more straightforward, because some of these can be kind of challenging. But let's go through another example. Pause the video, obviously, if you want to read through those. But let's go through another example where we use our use substitution. There it is. So we've got z's in this one. Integral of z times radical z squared minus 5 dz. Integral z square root z squared minus 5 dz. And it is often the case where if you have something grouped inside of a sine or a cosine, or as the exponent of an e, or in this case under a radical sign, that's going to be your u. Not always, but that will often happen. So in this problem, the thing to recognize, z squared minus 5, the derivative of that is kind of that term. Not perfectly. There's going to be a 2 we'll have to deal with in this one. So that's what makes this a little bit like one step more challenging than the last one. But let's see what happens. U equals z squared minus 5. The derivative of u, 2z times dz. All right, so what do we do there? I see the z dz, z dz, that's fun to say. I see the z squared minus 5. We're almost good, but what do I do with the 2? What do I do with the 2? Well, we're going to rewrite this 2 on the left-hand side. So I'm going to divide both sides by 2 and write 1/2 du is equal to z dz. Now all of the z's in the integral are accounted for, and I can write it all in terms of u's, but I have this extra factor of 1/2 that tags along with me. So let's see what this looks like. This is equal to the integral of, let's see, our z squared minus 5 is under the radical, so radical u, and then times 1/2 du, because that's times dz. Okay, so all of our z's are gone. Let's see, I'll draw circles and arrows. The z squared minus 5 is that, and then the z dz, those both went there. So what do you do with the 1/2? Well, that factors out of our integral. We don't have to worry about it. And then we're going to write our u raised to the 1/2 power so that we can use our power rule. Add 1/2 to the exponent and you get 3/2 over 3/2 plus our constant c. Now let's simplify and back substitute. 1/2 times, the denominator flips up, 2/3 times z squared minus 5, z squared minus 5 to the 3/2 power plus our constant c, and that simplifies just a little bit more. The 2's cancel out, and we're left with our answer 1/3 parentheses z squared minus 5 to the 3/2 power plus our constant c. And if you want to check that on your own, you can. Let's see what happens though. This exponent, if you take the derivative, this exponent comes down, the 3's cancel out, but there's still a 2 left. Keep the inside the same, subtract 1 from the exponent, and then take the derivative of the inside, 2z, that 2, that's where that 2 cancels out. All right, so that is the answer for this example. Let's take a look at this next example that involves an integral of some trig functions. So we have the integral of sine t over cosine cubed t dt. We're going to do some u substitution. The question is, what is u equal to and what is du equal to? There we go. So when looking at a problem with trig functions, notice that the cosine one down here, that one's got the exponent, and then the sine one up here, that one does not have an exponent. All right, so the approach that we want to use in this one is to set u equal to the denominators, just the trig part of it though, so not the cubed, but just the u is equal to the cosine of t. All right, so that's really important that you get that right. This isn't interchangeable. It doesn't work just as nicely if you set u equal to the sine of t. Okay, because then you would have like a du cubed, and that no, that doesn't work out well. All right, so this one we set u equal to cosine t, and the reason this is going to work out is that when I take the derivative of cosine, I get negative sine t dt. And hey, look at that, inside of the integral I have a sine t dt right there, and then the cosine cubed in the bottom is going to become u cubed. What do you do with the negative sign? That's right there. Well, if I divide both sides by -1, it essentially flips over onto the other side. -1 du is equal to sine t dt. You always want to have what you're substituting, the starting variable, to be expressed by itself on the right-hand side of the u substitution steps. Okay, that's going to make it easier. So if you have an extra 2 or a 3, divide by it, throw it on the other side. That'll make it easier in the long run for you. So let's make our substitution now. This is equal to the integral, the sine t dt, I already circled it once. That becomes du up in the numerator, or you could put it after the fraction. And then the cosine cubed t, that becomes u to the 3rd power. And I'm just realizing I forgot my negative sign. -1 times du, or just the negative sign. Ultimately, let's factor that out. Negative integral, the u cubed in the denominator, I'm going to bring that up with a negative exponent, u to the -3 du, and then let's use our power rule. Negative sign, u to the -2, because I'm adding 1, over -2, plus our constant c. Simplify and back substitute. The negatives cancel out. I'll pull the 1/2 off. 1/2 times what was u equal to? Cosine t. So cosine t to the -2 plus c. That would be an acceptable way to write your answer. I'd be happy with that. Or 1/2 cosine squared t plus c. So it's cosine squared because it's in the denominator, right, the negative exponent. So it just drops down to the denominator with the 1/2. Let's look at one last example, but this one is involving definite integrals. So hopefully you see right off the bat that my integral has bounds. So the answer is going to be a number, not a function plus c. That's a big difference in this one and the previous examples. Okay, and then the other piece that makes this different, or the other piece to be aware of, rather, is that these bounds right? The graph of this function, right? Those bounds are on the x-axis. Those are x bounds. So when we make our u substitution, we also need to substitute the bounds and find them instead of x, but in terms of u. Okay, so that's the new piece that we'll kind of add on with this last example. All right, so what do I set? Well, let me rewrite this. We have the integral from 0 to 1, x squared parentheses 1 plus 2x cubed to the 5th power dx. All right, if you look inside of the parentheses, that has a derivative on the outside of the parentheses. There's just going to be a coefficient that we have to deal with. A 6 it will be. Okay, so what we do is we'll take our u is equal to 1 plus 2x cubed du 6x squared dx. Derivative of 1 is 0. Derivative of 2x cubed is 6x squared. So the 6 we'll deal with the same way we did. It was a 2 in an earlier example. We'll divide both sides by 6 and write this as 1/6 du is equal to x squared dx. So I'm going to ignore the bounds for a minute. I'll come back to them, I promise. We'll say this is equal to, now I'll do my underlining. Let's see, x squared, circling, x squared dx, that is 1/6 du. So this is the integral, something to the 5th power times 1/6 du. What do I put inside of that parentheses? Actually, I didn't really need a parentheses there because that's just u to the 5th power. U is 1 plus 2x squared. All right, so what do we do with the bounds? Right? If I just had the exact same process as the earlier examples, this wouldn't be any different. I need to do something new now because I have the bounds. Well, the bottom bound in terms of x is 0, so we use our substitution to find a new bottom bound. And by that I mean, if x is 0, then u is 1 plus 2 times 0 cubed, which is equal to 1. That's our new bound. That's our u bottom bound. And then, if x is 1, the top bound, u is equal to 1 plus 2 times 1 cubed. 1 cubed times 2, add 1, you should get 3. So my new bounds, in terms of u, are from 1 to 3. And now we can just do this the same way we've done other definite integrals and say that this is u to the 6th over 6. Oops, write this down. U to the 6th over 6 times that 1/6, although I could have factored it out at the beginning, but I'll leave it right where it is. Evaluated over the bounds from 1 up to 3. So this is, let's see, it's going to be over 36. 3 to the 6th power over 36 minus 1 to the 6th power over 36, right? Top bound minus bottom bound. So then 3 to the 6th power is 729 minus 1 over 36. And if you simplify 728 over 36, you should get, let's see, I think 182 over 9 is the simplest form, or as decimal, I think it's 22 point a bunch of 2's or something like that. All right, that is it for that one. So notice we got a whole number, or not a whole number, but a real numbered answer for this definite integral. All right, so that is going to do it for this video. Try some of the homework problems. If you get stuck, please send me an email. Let me know which ones you're having trouble with. I'll either throw something in Blackboard, record something, put in Blackboard to help you out, or just, we can work one-on-one to do some of these. Please let me know if you're struggling. Thank you very much for listening. Have a wonderful day.